Hi, my name is Kwelo Okafor. This is my paper, Azure Accelerated Networking, Smart NICs in the Public Cloud. This paper was put forward by Microsoft. The rest of these slides have the audio pre-recorded, so please go through them and enjoy. Thank you. The breakdown of the paper is as follows: Introduction and background, design goals and rationale, Smart NIC hardware design, AccelNet system design, the performance results, operationalization, experiences, conclusion, and future work. Introduction. Cloud services require a lot of computing and network resources. This is a well-known issue, and as a large public cloud provider, Azure has built its cloud network on host-based software-defined networking technologies. Cost of providing services by running software on hypervisors continue to increase. So they needed another way of doing things. A solution that could provide software-like programmability while providing hardware-like performance was required. That was the best case scenario, and that's what they were looking to do when they developed SmartNICs. Solution was Azure Accelerated Networking, AccelNet, Microsoft Host SDN stack implemented on the FPGA-based Azure SmartNIC. Microsoft had design goals and rationale to meet to design the AccelNet system. Um, the virtual private filtering platform was Microsoft's cloud-scale programmable vSwitch, providing scalable SDN policy for Azure. And they noticed that many performance bottlenecks caused by doing packet processing in the hypervisor can be overcome by using hardware that supports SR-IOV. Knowing that their design goals were don't burn host CPU cores. Since there are fixed costs per server, the best way to lower the cost of a VM is to pack more VMs onto each host server. Using even one physical core for host networking is quite expensive compared to dedicated hardware. Thus, running a high-speed SDN data path using host CPU cores should be avoided. They also wanted to maintain host SDN programmability of VFP. VFP is highly programmable, including a multi-controller model, stateful flow processing, complex matching capabilities for large number of rules, complex rule processing and match actions, and the ability to easily add new rules. The level of programmability should not be sacrificed for the performance of SR-IOV. In fact, they wanted SDN controllers to continue targeting VFP without any knowledge that the policy was being offloaded. Most SDN policies do not change during the duration of the flow, so all policies can be enforced in VFP software on the first packet of a new TCP/UDP flow, after which the actions for that flow can be cached on an exact match lookup. They wanted to achieve the latency, throughput, and utilization of SR-IOV hardware and support new SDN workloads and primitives over time. Also, roll out new functionality to the entire fleet. Customers should not have to move their existing deployments to new VM types to enable new features. They wanted to provide a high single connection performance. An explicit goal of AccelNet is to allow applications to achieve near peak bandwidth without parallelizing the network processing in the application. They wanted to scale to 100 gigabit. AccelNet was actually developed for 2015 generation at 40 gigabit plus, so they wanted to allow for future expansion given how data rates increase in today's world. And finally, they wanted to retain serviceability. VFP was designed to be completely serviceable in the background without losing any flow state and support live migration of all flow state with the VM being migrated. They wanted SmartNIC software and hardware stack to have the same level of serviceability. Microsoft considered different hardware options for their SmartNICs. They considered ASIC-based NICs, but they discovered that custom ASIC designs for SDN processing. Although it provided the highest performance potential, they suffered from lack of programmability and adaptability over time. In particular, the long time span between requirement specifications and the arrival of silicon was on the order of 1 to 2 years, and in that span requirements continued to change, making the new silicon already behind the software requirements. Multi-core SOC-based NICs traded some performance to provide substantially better programmability than ASIC designs. However, at higher network speeds of 40 gigabits and above, the number of cores increased significantly. The single flow performance, higher latency, and poor scalability at higher network speeds left Microsoft looking for another option. Now, FPGAs, which were the eventual choice, what made it most attractive for AccelNet were the programmability to adapt to new features, the performance and efficiency of customized hardware, and the ability to create deep processing pipelines, which improve single flow performance. They also considered the initial option of burning host cores, but they discovered that although they had more programmability requirements than ASICs, the cost and performance overhead of burning cores to VM hosts cost was sufficiently high, as outlined earlier. That said, when they pitched FPGAs to their design team, the design team had some reservations. They considered FPGAs were much bigger than ASICs, and they discovered that although that is true, it was reasonable considering the massive improved programmability and configurability of FPGAs compared to ASICs. FPGAs could have been more expensive, but Microsoft bought in bulk due to their scale requirements, so that helped. And FPGAs are hard to program, but it was manageable when they put the hardware and software teams working together in one group, and they also use software development methodologies like agile development as opposed to hardware project implementation like waterfall methods. They were concerned that FPGA was hard to scale to be deployed at hyperscale, and the code was locked to a single vendor, but these were later ironed out, and FPGAs were used. The figure shows the SmartNIC system architecture as a bump in the wire. The converged architecture places the FPGA as a bump in the wire between the NIC and the top of the rack switch, making the FPGA a filter on the network. A cable connects the NIC to the FPGA, and another cable connects the FPGA to the TOR switch. The AccelNet system design. For the software design, while the vast majority of the packet processing workload for GFT falls onto the FPGA hardware, software remains responsible for control operations. The figure shows the high-level view of the architecture. The flow table may not contain a matching rule for a given packet. In these cases, the offload hardware will send the packet to the software layer as an exception packet. Exception packets are most common on the first packet of a network flow, when the flow is just getting established. When the FPGA receives an exception packet, it overloads the VLAN tag in the packet to specify that it is an exception path packet, and forwards the packet to the hypervisor vport. VFP monitors this port and performs the necessary flow creation tasks after determining the appropriate policy for the packet's flow. If the exception packet was destined for a VM on the same host, the VFP software can deliver the packet directly to the VM. If the exception packet was outbound, that is sent by a VM for a remote destination, then the VFP software must resend the packet to the SmartNIC which it can do using the same dedicated hypervisor vport. For the FPGA pipeline design, there are four major pipeline stages: a store and forward packet buffer, a parser, flow lookup and match, and flow action. The parser stage passes the aggregated header information from each packet to determine its encapsulation type. The third processing stage is match, which looks up the rules for the packet based on the unique key from the parser stage. And the final component is the action stage, which takes the parameters looked up from the flow table and then performs the specified transformations on the packet header. And for flow tracking and reconciliation, GFT keeps track of all per connection bytes flow counters, such as TCP sequence acknowledgement numbers and connection states, and timestamps of the last time a flow got a packet. GFT must also perform reconciliation so that flow actions get updated when VFP policy changes. Microsoft measured the performance result with AccelNet. They measure various parameters, like 1-way latency between two Windows Server 2016 VMs using registered I/O sockets by sending 1 million 4-byte pings sequentially over active TCP connections and measuring the response time. They got 17 microseconds with P99 of 25 microseconds and P99.9 of 80 microseconds. With pairs of both Ubuntu 16.04 VMs and Windows 10 VMs with TCP congestion control set to cubic and of 1500 MTU, they consistently measured 31 gigabit per second on a single connection between VMs with 0% associated CPU utilization in the host. The figures show some parameters they measured, like latency distribution, single connection TCP throughput, Azure SQL DB average client read times, SDN gateway forwarding latency. They also compared AccelNet's performance to other public cloud offerings that and they measured on later generation Intel Skylake based instances. The figure shows the results, putting AccelNet's performance ahead of other providers like AWS and Google, showing latencies, tail latencies, and throughput. They also measured the power draw of the generation board, including all components in operational servers. They put it at 17 to 19 watts depending on traffic load. They noted it was well below the 25 watts power allowed for a typical PCIe expansion slot and on par with or less than other SmartNIC designs they've seen. The operationalization of AccelNet. Microsoft wanted to assure serviceability and they considered this right from the design stage, as mentioned earlier. For serviceability, TCP flows and the VNIX should survive FPGA reconfiguration, FPGA driver updates, NIC PF driver updates, and GFT driver updates without bringing down VFs and VMs. They achieved this by transparent bonding, which is shown in the figure. Transparent bonding between an SR-IOV interface and a synthetic interface. They also included monitoring and diagnostics, which is important in any future offered to the public cloud space. Microsoft's experiences building AccelNet were a lot. They observed the following goals. They stopped burning CPU cores. SDN controllers continued to add and program new policy in VFP. FPGA overhead latency was less than 1 microsecond. Addition of new actions to GFT on FPGA to support new workloads continued. They rolled out changes across multiple servers and SmartNIC hardware. Line rate achieved on a single connection. Design scales well to 100 gigabit plus. Servicing of FPGAs carried out for years without negatively impacting VMs. AccelNet has been running for over 5 years at the time when they wrote this paper. And the lessons they also learned was design for serviceability should be made upfront, which they did by including it in their design criteria and rationales. They used a unified development team since it was a hardware and software problem. They put the hardware and software people in the same area and they work together to achieve AccelNet. They use software development techniques for FPGAs. Better performance means better reliability. They noted that hardware software design is best when iterative. Taking it step by step and having a way to track back what you did. Failure rates remain low. The upper layers should be agnostic of offloads. This is important so that serviceability and other operations could be carried out, and the upper layers have no idea what is going on below and they continue to run as normal, and they mitigated Spectre performance impact. In conclusion, this paper detailed Azure SmartNIC and accelerated networking and the experiences Microsoft had building and deploying them. The paper described functions that were already done in software in host SDN and offloaded to hardware for greater performance. The future work will describe entirely new functionality that can be supported now that there are programmable NICs on every host.